Welcome back. In this video, we'll zoom in on how sensible and latent conditioning processes appear on the psychrometric chart, and why understanding them is essential for HVAC design and control. Here's what we'll explore in this short video. First, we'll talk about how sensible heating and cooling shift air temperature. Then, what happens when we cool below the dew point. And finally, how humidification adds moisture to indoor air. And why all of these matter when designing or analyzing an HVAC system. By the end of this session, you will be able to clearly identify sensible and latent HVAC processes on the psychrometric chart, recognize their unique directional patterns, and explain the physical change involved, including variations in temperature, moisture content, and a phase change when applicable. You'll also gain a better understanding of where these processes take place in real HVAC systems and how to interpret them for better system design and performance evaluation. Let's make it real. Imagine it's the middle of winter and the air in your home feels so dry, your skin itches and your throat is scratchy. What HVAC process could improve that? Now switch seasons. It's a hot, humid summer afternoon in a coastal city, and you walk into a nice, cool building. What's happening inside the system that makes the air feel not only cooler, but drier and more pleasant? These are sensible and latent processes at work, and the psychrometric chart help us see and control them. Sensible heating and cooling move air horizontal across the chart. The humidity ratio stays constant while the dry bulb temperature changes. We see here they move constant, and here the dry bulb temperature is changes. So heating is rightward and cooling leftward. You'll see sensible heating in systems like electric duct heaters or gas furnaces, where air is warm without adding moisture, ideal in cold, dry climates. For example, in a hotel room during winter, a duct heater warms incoming air before it enters the room, raising the temperature but not changing the moisture level. Sensible cooling is typical in spaces where moisture control is less critical, such as dry office environments. A cooling coil reduces the air temperature before it enters the space, but stays above the dew point, so no condensation occurs, just a drop in temperature. These processes are foundational to HVAC control strategies and play a key role in energy load calculations. The humidification begins like sensible cooling, but if air is cooled below the dew point here, water condenses. The path bends if the path if air is cooled below the viewpoint, water condenses, then the path bends toward the saturation curve, reducing both temperature and humidity ratio. Now here we reduce temperature and humidity ratio. This process is commonly seen in cooling coils of air conditioning systems, especially in humid regions. For example, in a coastal hotel when warm, moist air enters the system. It first undergoes sensible cooling until it reaches the dew point. As it continues to cool, moisture condenses on the coil surface and is drained away, reducing the humidity level of the air. Similarly, in hospitals or museums, where indoor air must be tightly controlled to prevent mold or protect artifacts, cooling coils are intentionally sized and operate to provide enough latent capacity to remove significant moisture from the air, ensuring both comfort and air quality. Humidification increases the moisture content of air. It can be done by injecting steam, raises the temperature and humidity, or spraying water, adds moisture with minimal temperature change. Both processes move the air up and to the right of the psychrometric chart. In HVAC system, humidification is typically used in climates or seasons when indoor air becomes too dry, especially during winter. For example, in a commercial office building with central heating, indoor air can drop to 20% relative humidity. A steam humidifier may be installed in the air handling unit to add moisture, improving comfort and reducing issues like dry skin, irritated eyes, or static electricity. Spray humidifiers, which add vapor, water vapor with a less thermal input, are often found in greenhouses where temperature must be tightly controlled. In HVAC design, we typically focus on humidification processes, but also increase the air temperature, such as steam injection, because they are more compatible with thermal comfort goals. While it is technically possible to humidify by spraying cool water, which can lower dry bulb temperature, this is rarely desirable in most building applications. Cooling the air while increasing its humidity can lead to discomfort, promote condensation on surfaces, and make climate control harder to manage. As a result, HVAC systems generally apply humidification during comfort and during heating periods when adding both heat and moisture helps maintain comfort and indoor air quality. For example, during winter in a cold climate, adding moisture to heat the air avoids dryness without overcooling the space. Why is this important? HVAC systems condition air by changing its temperature, humidity, or both. Each process leaves a distinct trace on the humidity chart. Understanding these traces helps you to diagnose system performance, design better air handling strategies, and predict thermal comfort outcomes. This foundational knowledge will support everything from system sizing to energy control. Let's summarize what we have covered. Sensible processes change the air temperature without adding or removing moisture. Think heating in winter or dry cooling in summer. Latent processes involve moisture transfer, like humidifying dry winter air or dehumidifying a humid summer day. Dehumidification is usually achieved by cooling air below its dew point, leading to condensation and moisture removal. Humidification adds moisture to the air, often done during heating to improve to improve comfort. Each of these processes follows a distinct path on the psychrometric chart. Recognizing them helps HVAC professionals design systems that not only meet performance goals but also ensure indoor comfort. Next, we'll explore evaporative cooling and air mixing, two processes that often occur in passive or hybrid systems. These involve different principles but are equally important to understand using the psychrometric chart. Thanks for joining me. See you in the next video.